All right. Hi, guys. Just a quick intro before we get started. My name is Rushi. I'm the president of Illinois Robotics and Space. A few things about me. I'm 20 years old. I'm from San Jose, California. I go to school at the University of Illinois. I'm getting a dual degree in mechanical engineering and physics with a minor in astronomy. This is kind of what I like to do, building rovers. So my hobbies are hiking, podcasts, stargazing, and watching movies. Yeah. So kind of what the goal of this presentation is before you guys get started with our activity today is give you kind of a little bit of an in-depth look at NASA's Artemis program, because the competition that we participate in is kind of under the umbrella of the Artemis program missions. And kind of the Artemis, has anyone heard of the Artemis mission? Oh, that's going on. Okay, that's cool. That's good. It's kind of a revival of the earlier Apollo programs that happened in the 1960s, 1970s. It's been quite a while since we've been back to the moon with a human. The last human visit was 1972, so it's been many years. There's a lot of controversy around the Artemis program because many people think it's a waste of resources. Why are we trying to go to the moon if we're trying to go to Mars? Many people don't see the point, but kind of going to Mars is step 20, and we have to get everything beforehand. And one of those steps is making sure that we have a regular presence on the moon, making sure that we can host humans in a habitable zone for however long that we want to stay on Mars. If we can do that, then we can do that on Mars. Because going to the moon is like a 3-day trip, but going to Mars is well over a month, I believe. So if something goes wrong there, it's bad. Something goes wrong on the moon too, it's bad, but it's worse if it's on Mars. The original kind of conception and idea for the Apollo missions was obviously the Cold War, if you guys know about that. Russia, Soviet Union, not Russia. But it was still an era of science and innovation. We learned a lot. We built a lot of cool rockets. The Saturn V was the famous rocket that came out of that era. And they're building a new rocket for the Artemis program. That's kind of the champion rocket for this new era of moon lunar space travel. In order for you guys to get a closer look at kind of what that looks like, NASA actually has a video explaining much better than I am the Artemis program and the rocket that's being used for that. It is a little bit technical, so apologize. They talk a lot about the orbits and stuff like that.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind: the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts: the crew module, where up to 4 astronauts will live and work throughout the flight; the service module, with life support systems for the crew and its own engine and fuel reserves; and a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there was no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released. The module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
All right, so in the Martian, kind of one of the key things that allows, I forgot his name, to survive, is the fact that he's able to use resources from other future Mars landing missions. And that's the whole idea that's being used in the Artemis mission also is preloading the moon, kind of sending rockets beforehand and putting supplies there on the surface of the moon in different locations at the landing sites, which drastically reduces the amount of weight that the rocket has to carry. It doesn't have to carry all the supplies that you need for the habitable zone and everything. The astronauts kind of just go set it up, like Lego pieces basically, and live in there. So yeah, the use of going back to the moon, it's kind of crucial to understand, how we can establish a presence and kind of allow for more commercial trading and stuff like that to happen on a non-Earth entity body. Yeah, and also the moon has a lot of secrets still that we haven't solved yet, like the origin of the solar system is still mostly kind of figured out, but still not. If you are interested in astronomy, which I hope you are, you can continue on, and hopefully in college you would take, planetary sciences, where you kind of talk about different theories of how the moon was formed. One of the main theories is that a huge kind of thing crashed into the Earth, and then the gravity of all the little pieces combined to form the moon. That's a strong case for that one, but we still don't know yet. So there's a lot of secrets that the moon still holds, and kind of how moons form, how something can go from being dust in the galaxy to being a planet where humans can live. Is still up for debate. Yeah, but I think the main kind of purpose of that video was to show that like everything that happens with the future of space travel, the future of civilization, these more broader questions, it has to do with engineering. I mean, it's all engineering. Obviously there's other STEM fields involved, but it's very much engineering heavy, building a rocket, calculating trajectories of the home and transfer orbit, things like that. It's very much engineering and computer science focused. So it's definitely, the industry that's up and coming, been up and coming, and still is up and coming for the last 50 years. And it's definitely a very, very interesting field. The work I do in engineering, which I'll show you now, is very fun. I absolutely love it. What we do is participate. Oh yeah, sorry. Yeah. The ocean. So everything is launched off of Cape Canaveral, Florida, in the Kennedy Space Center. And once it launches, it'll fall into the Atlantic Ocean, basically. And I believe it's the Coast Guard that picks it up, but I'm not entirely sure. The Coast Guard picks up the humans. No, that all of that is calculated. The orbit and everything is calculated to make sure that it's over the ocean when it destages the external components. Yeah. Well, I'm sure the astronomers. I don't know. Yeah. Probably. Yes, there's also that too. That's a good point. Yeah, so like the gateway that was talked about in the video, if you remember The Martian, there was like the thing orbiting Mars. It was just continuing orbiting Mars. It's the exact same thing. It's going to happen with the Artemis mission on the moon. And, like your teacher said, it's going to be like kind of a halfway point also between the moon and the Mars. I believe it's so that, astronauts can get more acquainted to space before they go to Mars itself, because it's on the video, going to Mars is a 6-month journey, but going to the moon is a 3-day journey. So you can get acquainted more with the microgravity and stuff like that. Yeah. That's a really good question. I don't know. Going to Mars is at least 15 years, I think. So you guys, if you're interested, you could definitely be a part of the team that, yeah. Actually, one of the alumni of our robotics team, do you guys, oh, you probably won't, but there's a really famous space probe called OSIRIS-REx. Oh, cool, nice. OSIRIS-REx is a really famous space probe because it was the first one to land on an asteroid and collect samples off an asteroid and bring it back to Earth, which is, something we've never done before. It was done recently, and an alumni of our robotics team was on the vision controls for the robot that actually extracted the material from the asteroid, which is really cool. So, yeah.
So it's like related to the planet. So like if it was dust, right? And it created a fin, how did animals?
That's a really good question. You should take extraterrestrial life. It's a really cool field, astrobiology. One of the main theories that I like is called panspermia, which is the fact that if you look at our elements and the elements of the universe, hydrogen, oxygen, nitrogen, carbon, honk, it's the same common elements in the entire universe. So you and I, everyone is made up of the same common elements of the universe. So the theory is that an asteroid holding key minerals like olivine and things like that landed on Earth, and it was just the right kind of environment for it to create microbacteria, stuff like that, and then that evolved into humans. So that's panspermia, is that we're aliens. That's kind of we're not from Earth, we crashed from an asteroid, basically. Yeah. Yes, asteroids, yeah. Yes. That's a great question. There's a name for this thing. The Royal Society for Astronomy, I believe it's what it was. It was like recently when Pluto was kicked off the planet team. They kind of redid the definition of a planet, and that kind of extends more also to the moons. But the definition of a planet is three things it has to orbit a sun or a star, so that moons can't be planets. It has to be round, which means that it has to have enough gravity to be round, because asteroids are small. It doesn't have enough mass, enough weight to be able to kind of crush itself into a ball, but planet does. And the third one is it has to have cleared its neighborhood, which means that there can't be other small objects around that planet, because if it's big enough, more massive enough, its gravity will pull all that in to make the planet bigger. So that's why Pluto was kicked off, because it's in this thing called the Kuiper belt, which is where the comets come from. So it's outside has kicked off the planet team. Yeah, I'll go to you. Yeah. Well, we did, but like I was talking about like very, very, very beginnings. Like, yeah, like very beginning, like single-celled particles. You know, monkeys came many billions of years. Billions, maybe billion, like 1 billion, maybe. Yeah, yeah, yeah. There's 3 eukaryote, prokaryote, and archaea. Actually, the Carl Woese discovered archaea, and he was from University of Illinois. There's a whole school named after him at the university. Yeah.
Okay, so like when we coded, and what did they do? What did that do?
I'm not entirely sure. There was other projects going on, like the rover landed on Mars, the Perseverance rover, in 2021. Because I was in physics class when it landed. And recently, the James Webb Space Telescope was going up. I'm not too sure about what the Artemis was going on with that, but that's a good question. Yeah.
So I was asking you about the to just try to understand this. Why are the landings so why isn't the technology
Oh, well,
just trajectory?
the Mars Perseverance rover was actually one of the cleanest landings ever with the parachute, and the Perseverance has the drone Ingenuity is what I think it's. So that was like, I think drone technology is starting to evolve to kind of drop the lunar end, but it's just difficult because if you have something that's going so fast, it's hard to slow it down. That's kind of just the main thing, and also like it's easier on the moon because there's no atmosphere, so there's not going to be much turbulence. But like in Mars, there is an atmosphere. There is a very small atmosphere, but there is, so that can cause turbulence, and you can't account for everything. They could just happen to have a dust storm at that exact second, because that happens a lot on Mars. Yeah. Okay. I'm going to take one more question, and then we can ask at the end. I'll go to you because I have actually questions. Oh, you're right. I believe it has to do. It's a very fine line. A piece of debris. I mean, it's a satellite. A moon is called a satellite. Like satellite is anything that orbits something. So technically, like all the like space junk, they're all technically moons, but we only have one moon. I don't really think there's a line. It's ambiguous on purpose, I'll tell you that. Technically, yes. But on that front, I believe the difference that is invoked is spherical versus non-spherical. An asteroid is typically non-spherical except for a couple exceptions, and a couple moons like, oh yeah, Mars. Well, yeah, Mars is Phobos and Deimos is not round, but I don't think there's enough debris to like have like 1,000 moons. So I think it's ambiguous on purpose. Yeah. Okay, I'm gonna move on because there's a few more slides before we get to the activity for the day, which is a more fun part. But I'm glad you guys are asking questions. That's cool. Yeah. So like I said, engineering is the front of all of this technology, and if you want to go to Mars, it's gonna be with engineering, and that's kind of what we do on this team. We're a NASA team, so we participate in the NASA Robotics competition, and this competition is essentially a lunar mining competition where an autonomous lunar rover that we build goes through this first gray area that's in the front, kind of using its vision system to navigate through craters and boulders that are randomly placed. And then once it gets to a safe area over there, the excavation zone, it locates the best possible place to dig. It digs underneath 30 centimeters of topsoil called BP1, collects the gravel, which is called icy regolith, underneath that BP1, collects it and brings it back. And all this is done autonomously. And the purpose of that autonomously is because you're not going to have a driver sitting in mission controlled controlling a robot that's so many millions of miles away. It's just not feasible because the main thing is time delay, because light doesn't travel that fast, and your radio is a frequency of light. The light speed of light is finite, and you're going to have a delay. I don't remember. I think it's a couple seconds for the moon, but it's still enough to, if you're driving and you don't see a crater, if you have a couple seconds delay, you could have already fallen in the crater in that couple seconds. So, and on the Mars, it's like 30 minutes or something like that. It's quite a delay. So you can't have a 30-minute delay if you're trying to drive a rover. So that's why autonomously is a very key component in this competition. But besides that, we have 2 other parts of the competition, which is the systems engineering report, which is, everything done in NASA is done very structured and very, calibrated to make sure you're optimizing your time, your engineering resources, and testing safety. And all of that is done through systems engineering, which is a field of engineering that basically manages other principles and makes sure that everything is going according to plan. So NASA has a whole systems engineering structure that they run every team with, and we implement that system engineering structure into our team to make sure that we're, doing things efficiently and to the best of everyone's capability. And the last component is the outreach, which is, talking to you guys. It's really fun. I personally love doing outreach. Yeah. Are you guys interested in looking at a rover? That video is from a previous competition. You can take a quick look. This is, yeah. So this is one of the rovers. I'll just show a few minutes of this. But this is one of the rovers. It's autonomously driving right now. And yeah, so this is NASA hosts this competition in a simulated lunar environment in the Kennedy Space Center. So we actually go down to Kennedy Space Center and you go into this pressurized environment. So you can see the people are wearing suits because the BP1, that sand, if it gets in your lungs, you're screwed. You're absolutely screwed. It's like a dust, so it's not safe to be in that environment without a hazmat suit on. Yeah, I don't know what this is, but maybe I'll skip ahead to the digging. Okay, so they're unloading what they collected. So they already dug the hole. I skipped too far ahead. But they dug the hole over here. They collected the regolith, and then they brought it back, and they're dumping it over there. So that's one of the things. This is one of the designs. Our design is different. All right. Oh yeah. How our team is kind of structured, what we do, IRIS stands for Illinois Robotics in Space. Basically, our team is divided into 5 subcomponents, 5 sub-teams. We have the mechanical sub-team that does all the design work, all of the machining, manufacturing, mechanical's the best. And then there's the autonomous sub-team that kind of does the vision system and makes sure that, this thing has a brain. The electrical sub-team does all the wiring and manufactures all the electrical boards. And then the systems team, like I said, focuses on making sure everything's structured, writing that systems engineering report, which takes a very long time. And we have our outreach team that, comes and talks with you guys. This is our robot from the engineering open house that's hosted by the University of Illinois. We built a sand pit and, we're digging a little bit there. That was from last year. We'll be doing that again. So if you guys are interested, you can come end of March to the University of Illinois. We'll be hosting. Oh yeah. You guys can see our robot. Hopefully it works. All right. One of the other main components of this presentation is kind of to show you guys how you guys can get involved into engineering. And, the best way to do that is to understand how I got involved in engineering because I'm the best. So I'm from the Bay Area, from San Jose, California, which is, rampant with scientists and doctors and engineers. You can't go 2 doors without seeing one of them. So my dad's an engineer, my mom's a physicist, and my grandpa's a doctor. Just a lot of, cool. So I had an early influence from a young age. My dad and his dad used to build RC planes, so I used to do that with my dad as well. Build planes, trains, and cars, everything RC. So that's kind of how I got involved a little bit. Yeah. These pictures over here are all the planes that me and my dad have built. Pretty cool. I like them. And yeah, I was always interested in astronomy from a young age. Looking at, you guys know what Yosemite National Park is? Okay, cool. You guys are cool then. So that top picture is Yosemite National Park in the summer months, where you can actually see the Milky Way from the park. And it's really cool to see the whole cosmic dolphin is what it's called, because it looks like a dolphin. You can see it in Yellowstone. You can see it in any national park. The national parks are all dark sites that are away from city lights. So you could see the stars pretty beautifully. So yeah, I got really involved with that. And also because I live 15 minutes from the NASA Ames Research Park, which is where the concept of the space shuttle was designed. So I got a lot of tours from a very young age. So I had a good influence. My dad and I used to do a lot of Legos. So there's that too. Legos are always if you go in the engineering, mechanical engineering, if you go to every second person, you'll see they did Legos as a kid. So Legos are a huge way to get involved in engineering. And I was always building something. I always liked building. Me and my friend, my neighbor, we built a go-kart and I crashed and broke my arm. We built a zip line and I fell off the zip line and broke my tailbone. We built a tree house and I broke my leg falling off. I break a lot of things, but be safe when you're building things. Please don't hurt yourself. It wasn't good. It wasn't a good tree house. Yeah. And then when I got into 8th grade, got into circuitry. I learned a little bit basic circuits. So that kind of opened up a whole new thing where I could build my RC planes, trains, and cars from, something that a battery would power instead of me pushing it down my staircase. Yeah. I tried not to. Yeah. And then in high school, I did a lot of stuff. Are you guys familiar with FLL, First Lego League, or First at all? Okay. Well, it was a huge thing in my area.
It was huge here.
Oh, really? Okay. Yeah, it's a really big thing. Every school in my area has a first team of some sort. You know, for you guys, in middle school, you guys could do first tech challenge or first Lego League. Once you go to high school, you guys do first robotics competition, which is building these huge 120-pound robots to battle with other robots. It's not battle bots. It's not battle bots. It's not battle bots. You don't actually attack the other robots. You get a technical battle. But yeah, it's a game. You play the game and you get points. So it's really fun. I got involved in that. I was one of the mechanical engineering directors for that, and I built a lot of things. And I was also a machinist for the team, so I got into manufacturing and how to actually make the things I design, which is very important. Because if you don't know how to make what you design, it's not going to be made. Yeah. And I also got into science fairs. I was big into doing science fairs. I did a lot of chemistry ones. Yeah, and I also really enjoyed teaching STEM. I actually taught 300 hours plus of STEM to middle and elementary schoolers like you guys over the course of 2 years. I taught 300 plus hours. Yeah. And also Toyota hosts this thing called the Hydrogen Horizon Automotive Challenge, which is this car over here, which is a hydrogen fuel cell car. So I built a fuel cell, which was pretty cool. And it worked until I broke it. Yeah. Oh, that's the challenge. It's hosted by Toyota, where you build this hydrogen fuel cell car. It's a great question. It's a different type of energy that's powered from H2 gas instead of like fuel, regular gasoline. It's clean energy, but also could be unsafe because hydrogen is explosive. Yeah, but this didn't explode. That's not how it broke. I accidentally ran it down my staircase. Yeah, I don't know. And now in college, I'm involved with Illinois Robotics in Space. I love it. I love, designing the parts, making the parts. Making the parts can be somewhat hard because I do injure myself a lot. Be safe, guys. Be safe, please. It's painful. Yeah, and I'm also involved in the American Society of Mechanical Engineers. Me and my roommate started the product development committee, so we, make products and are trying to market it. So that's pretty cool. We have a maker space in the mechanical engineering department, and that's what this picture is over here. And we just got 60 new printers, which each of them cost $7,000. So we got a personal grant of $100,000 from a donor. So he bought us these 3D printers at the top of the line. Very cool, very great. Also in the Astronomical Society. And the research that I do is working on a stratospheric balloon. So it's kind of the triple point between physics, mechanical engineering, and astronomy. What a stratospheric balloon is a bunch of instruments inside this thing called a cryostat, which is this red thing over here, which kind of keeps your instruments at a very cold temperature because it's called cold optics. It can't work unless it's at like 4 Kelvin. It's very cold. And you send it up from Antarctica. It's sent in a balloon and it stays up there for 20 days, and then it comes crashing down. Yeah, and I also tutor people because I like teaching. My Lunabotics experience personally, my freshman year, I was on the excavation team. So our mechanical robot is designated into 3 components. We have the drive base, which is the wheels and the chain and the gears, the bare bones of the car. We have the collection system, which is where everything is stored before it's brought back to the final collection dump site. And we have the excavation system that actually goes into the ground and digs and does everything like that. So I was on the excavation team building kind of this component of it that kind of goes into the ground and digs. And then my last year I was the lead of the mechanical team, and now I'm the president. And being in this team has very much influenced me into going into a PhD in physics, doing instrumentation, which is kind of building robots basically, which is pretty cool. Hopefully I get in. We'll see. All right, now what you guys could do to get into STEM, specifically the Artemis mission programs. NASA competitions like Lunabotics is very great exposure, obviously, to real engineering, real systems engineering practices, and real engineering practices. But it's also really good on a resume. I'll tell you that. It's very great. Yeah, and there's a whole bunch. If you just search up Artemis mission challenges, you'll get a whole bunch of them. And there's a lot of middle school programs as well. So you guys could get involved right now if you wanted to. All right, and now this is my final slide. But today we'll be doing Lego Mindstorms. Have any of you guys done that before? All right, perfect. You guys will get good exposure. I'm kind of building this robot first, is what we're gonna do with Legos. And then this kind of brain of the robot is called an EV3. And that's where all code is stored, and the code that we're gonna be doing today is drag and drop code. So it's not like a programming language. It's what was that? It's not a game. Yeah, it's like block programming is what it's called. Yeah, so you like make a block and then like there's a motion block and you can specify your wheels to move for a certain amount of time. Yeah, yeah. Well, that's good. That means you can do more things with the programming. It is fun. It's great. I did it and I have taught 3 teams for 3 years on how to do this. So yeah, thank you guys for listening to my presentation. I hope it was not disengaging.